So, hello everyone, this is lecture 5 for the nuclear physics. In the last lecture, we were discussing about the nuclear props and we are seeing that how charge is distributed inside the nucleus. And today we will see the binding energy. But before that, we have two more things, that is how charge is distributed inside the proton and how it is distributed inside the neutron. So, first let's study them. So, here in this y-axis, you have charge density and here you have the distance from the center. So, see, if you see this graph, then it will show that initially at the center you have zero density, then a little bit distance will give you the maximum maximum charge density, and this distance is very much small. From this graph I am just showing that it is increasing, but it is very much close to this center and it is increased to the maximum, then it decreases exponentially. So that's how this curve will be there. So you just need to know that how this curve will be for the proton. So to find the charge density or charge distribution inside the proton, we require a beam of electrons having energy of order of 1 giga electron volt. At center, charge density will be 0. Close to the center, it rises to the maximum value and then decreases exponentially as exponential minus r by a, where a is approximately 0.23 Fermi. So you must remember this graph, and that is all you need. So next is charge density inside the neutron. So see, neutron, you see that it is a neutral particle. So it is not a, means it is neutral, but see, there are positive and negative both charges inside there and they are in the equal amount. That's why it is giving you the neutral. So how it is distributed inside the neutron, that so that it is becoming the neutral. So this is your graph, that first in at the center you have the zero density, then you have the positive charge maximum density, then it will decrease and there will be a negative charge density, then again there will be a feeble layer of positive charge. So that's how this curve will be, means center there will be 0, then positive charge, then negative charge, then again a small layer of positive charge. So that's how the neutron is formed, and this maximum distance is up to 2 Fermi. So the charge density of neutron consists of an inner layer of positive charge surrounded by a large layer of negative charge, which is again surrounded by a feeble layer of positive charge. However, net charge of the neutron is 0, so that's how the neutron is made. So you must remember only these things as I told you. Okay, so today's topic is binding energy. So what is binding energy? See, when there is a system formed, then that stable system requires some energy to break. So that energy is called the binding energy. Exactly, means you have nucleus, and a stable nucleus requires some energy to break into the constituent particles. So that energy is called the binding energy. Like you can take this example. This is X atom and it has mass number A and Z is protons. So A is 6. If A is 6, then there will be 3 proton, 3 neutron. So there will be even energy required to release this first nucleon. Then for the second one, E2, for third E3, and for E4, E5. Then there will be only one remaining. So that's how you can distribute or break this whole nuclei into its constituent particles. So the sum of this whole energy is called the binding energy that requires to break down this nucleus into its constituent particles. So total energy required to break a nuclei into its constituent particles is called the binding energy. So there is one more way to see this thing, that how binding energy is defined. See, when a large number of particles come together to form a nuclei, then there will be some energy is lost. That energy lost means there will be a less energy. Now there will be some positive energy required to break this combination, means these particles come together and some energy is lost, and this energy is lost in the form of lost mass of those particles, and that's how the nuclei form. So it will give you a stable structure, and now that energy lost, that amount of energy is required to break them again into the constituent particles. So that energy lost is called the binding energy, and that comes from the mass defect, that is comes from the nuclei and its constituent particles. So we can also define binding energy in another way as follows. To form a nucleus, a bounded system, protons and neutrons, or protons and neutrons, some energy is lost. Lost energy is called binding energy. This lost energy comes at the cost of losing some mass of the constituent particles, called the mass defect. This mass converts into energy and give rise to binding energy. So if you see the, means there will be constituent particles, sum them up, and there will be mass of the nuclei. So you will see that these masses are not same. The mass of nuclei will be less as compared to its constituent particles, and that mass is loose in form of energy, and that is binding energy, and that comes from the, and that mass difference called the mass defect. So delta M will be Z MP, that is mass of proton, and this is number of protons. A minus Z will give you mass of total number of neutrons, Mn, that is mass of neutron, minus M of nuclei will give you the mass defect. Now from the Einstein equation, mc square will give you the energy associated with the mass defect, that will be delta mc square. Now see, if it is given, this mass is given in the atomic mass unit, then you just need to multiply with 931.5 mega electron volt. This will give you energy in mega electron volt. So you must remember this formula. In place of mass of nuclei, mass of atom is given, then what you will do, you need to just calculate the mass of nuclei, that is mass of atom minus mass of electron. So you can use this m atom minus Z m mass of electron. Now see, there are two cases. If binding energy is greater than 0 and binding energy is less than 0. If binding energy is greater than 0, then we will say that nucleus is stable, and there will be some energy is required to break this nucleus. Or positive, then nuclei will be stable because we have to supply energy from outside to disturb the nuclei into its constituent particles. Now see, if it's like something you can see that there is the bounded system like sun and earth, so there will be earth is rotating around the sun and it has the negative total energy. So now to free this earth from this solar system, you need a energy that will make this negative energy zero. So that's how you need to provide the energy. So that energy is called the binding energy here also, like to emit this particle out of the nucleus. So if binding energy is less than 0 or negative, then nucleus will be unstable and it will disintegrate itself. Means now negative will give you a less stable nucleus, so that means it will break down itself and become stable, and it will disintegrate itself to achieve the stable configuration. So there will be things we will study in the future, that how it disintegrates. So it will disintegrate into the with the help of means alpha particles, beta particles, gamma rays, gamma photons. So that's how it depends that how big or the unstable the nucleus is. So that depends on that how it will disintegrate. Now see, we have the binding energy, but see, as large number of nucleons will be there, so large binding energy will be there. Now how can we compare the two atoms, that which is more stable or more strong and another is less strong? So see, if this you have lithium, this is 7, and this uranium is 235, so you will see that binding energy will be greater for this and less for this. But that is not something which by which we can compare. Means you can't just compare the monkey with the turtle. So you just need to make them equalize. Means some parameter is needed to compare them. So see, if we calculate binding energy per nucleon, that will give us a single parameter which can be compared. Means we can use that to compare the different nucleus. So for the lithium, it will be binding energy per divided by 7 and binding energy uranium divided by 235. So it will give you binding energy for average binding energy for one nucleon inside the nuclei. Now we can compare that with the other atoms also. So that's how this new parameter is defined, that is binding energy per nucleon. Average, this is nothing but average binding energy possessed by a nucleon, single nucleon, is called the binding energy per nucleon. This parameter is used for the comparing the stability of different nucleus. Now see, we have this parameter, so we will just draw a graph for different atoms and their binding energy per nucleon, and that graph will give us that which is more stable and which is less stable. So this graphs comes from this observation. We calculated the binding energy per nucleon for all the particles or all the elements. So this graph you get, here you have A, that is mass number, here you have binding energy per nucleon. So as the A increases, initially it is increasing sharply, and up to 30 atomic mass number you will get 3 kinks here. This is nothing but helium, carbon and the oxygen. So you will see that they will be more stable as compared to the neighbor particles. So what is the reason of this stability? We will see in the cell model, and there we will see that there are even number of neutrons and protons that will give them, because of the complete pairing, that will give them extra stability. So we'll study them in the cell model. Now see, this will be become most, means the maximum energy or the binding energy per nucleon will be for the Fe that is 8.8. so that will be the most stable state, and again it will decrease slowly, and here you will see that up to this range it will remaining a little bit constant up to 8.5. So that's how. Now see what observation we can see from this graph. From this figure one can observe following aspect. For lighter nuclei, binding energy per nucleon is small. This is small. It rises sharply as A increases and achieves the maximum at Fe56. On the lighter nucleoside, there are 3 kinks, that are these, as I told you in the plot, which says that these particular 3 nuclei have the higher binding energy per nucleon as compared to their neighbor. These nuclei are helium, carbon and oxygen. Later on the basis of the cell model, we explain with this extrastability on the basis of the pairing. These 3 nuclei are even nuclei, and their protons and neutrons are paired up. This complete pairing provides extra stability to nucleus. So that's how I told you already. Around the maxima at Fe6, one observed that there is a broad peak around from A30 to A120, over which average binding energy per nucleon is 8.5, and it will remain same. For the broad peak is 30 to 120. So this will be average around remaining same. Later on, Weizsäcker defined volume energy term. So this Weizsäcker formula we will study in the liquid drop model, that how we define the binding energy, and that is called the semi-empirical mass formula. So Weizsäcker gave that. So defined volume energy term, as we already seen here. So this is how you are making the base of cell model. So previously we have seen this formula for the binding energy. So this volume energy terms given by the Wissaker for the binding energy, and these are the correction terms. So we'll see them how they will come in the liquid drop model. So Wissaker defined the volume energy term on the basis of this fact that binding energy per nucleus is constant over a significant range of A value. So that is given by because of this constant thing for a large range. So binding energy given by as volume energy term, that is AV. This is some constant A that is depending on the mass number. So that's how he gave the binding energy. Then there will be these correction terms came. So we'll study them in the liquid drop model. As A value increases or heavy nucleoside, binding energy per nucleon start decreasing. It becomes 7.6 mega electron volt per nucleon, around equal to 238. Now in the next lecture we'll see the explanation of this graph, and we'll move forward to the liquid drop model. So thank you everyone.